Hiya Nines. So in this, our first lesson of our algorithms module, our big question is how do computers use algorithms to sort and search for data? Today we're going to be talking about the three computational thinking concepts. In actual fact, I'm going to take you through everything that we're going to do in this unit of work. Today we're going to talk about computational thinking and in particular abstraction, decomposition, and algorithmic thinking. In next week's lessons, we're going to talk about searching algorithms like the linear search and the binary search. And we're also going to talk about sorting algorithms like the bubble sort, the insertion sort, and the merge sort. First, though, we're going to talk about computational thinking. Computational thinking allows us to take complex problems, understand what the problem is, and develop possible solutions. It's all about the ability to think logically through a problem. That does not mean that it's computer science specific. You can do this with any problem, in any walk of life, in any subject, and it will get you to a solution in the most efficient way possible. There are technically four strands to computational thinking. For us, though, in OCR computer science, if you ever would do it in year 10 and year 11, uh, it's only abstraction, decomposition, and algorithmic thinking. But the cousin of it is pattern recognition. That's really beneficial when you are solving problems. And we're going to come to that later on. Let's start though with just thinking about what algorithms are again. They're a set of instructions for solving a problem or task, right? And that task could be anything from making a chocolate cake to summing the numbers from 1 to 1,000 to building a Lego model. Uh, Regardless of what those instructions are, as long as those instructions get you to get something done, that is an algorithm. One strategy for solving large problems is to first try to solve a similar but smaller problem. Let's try and think about how to solve a jigsaw puzzle. If you had to describe to a 5-year old or to an alien about how to go about solving a jigsaw puzzle, what would you say? Well, you might say things like, well, first off, we have to take all the pieces out of the box. Secondly, we have to turn them all so they're the right way up. You might also say that you then find the edges and the corners. You might then go, well, from that, you can band colors together as well. And depending on the picture that we're trying to make, we can categorize those and figure out where they're going to be on our picture. The fact is that doing a jigsaw puzzle is algorithmic. Even though it seems like it's a bit randomized, really the steps that you go through to try and solve it is just a list of instructions. Algorithmic thinking is creating step by step instructions on how to do something. If you're using a computer to find an answer, you have to figure out how to solve a problem first and then write down the steps. We're never able to just go onto a computer and start coding without having a basic picture of the steps that are needed to create the solution in our heads. Algorithmic thinking gives us the ability to put those steps in a logical order so they make sense. But not all solutions are equally efficient. Let's take this problem: divide and conquer. You're going to, or you have already, played this game where one of you writes down a number between 1 and 1,000 on their whiteboards, and the other person just guesses. And the way they guess is by asking a question: is the number greater than whatever the number is? Like, is the number greater than 200? And then the other person can either say yes or no. If the number was 200, they just say, yeah, that's the number. How many guesses would you actually need to find the number? I'm betting that when you played this game, some of the times you took 5 guesses, but most of the time it was about 15 or 20. Would it surprise you to say if I said that actually there's a maximum number of tries that it should be? And actually, the worst case scenario is that it would take you 10 guesses to guess any number between 1 and 1,000. What you need to do is search for the midpoint first. You say, is the number greater than 500? If the other person says yes, then you know that it's between 500 and 1,000. If, sorry, 501 and 1,000. If the other person says no, then you know that it's between 1 and 499. In our first guess, we have eliminated half of the list. And if in every guess you eliminate half of the list, then it actually only takes 10 guesses to get down to one number. So in the worst case scenario, that is how many guesses it would take. So using that analogy, let's imagine that someone wrote the number 1 down as their choice. This is actually how it would happen. You go 500, then 250, then 125, 63, 32, 16, 8, 4, 2, 1. There you go. 10 guesses. Another computational thinking concept is abstraction. Abstraction is all about removing unnecessary detail from a problem so you can focus on the essentials. It allows us to figure out what is important in the problem. The only things that are important should remain in, and everything that isn't, we really want to just ignore. That's really prevalent when you're doing uh, verbal reasoning in maths problems and stuff. You know, you've been doing that since primary school. Those questions where it's all about, Alex has 10 apples, but Susan takes 8 away. How many apples is Alex left with? Well, it's not about the apples, it's about the numbers. So you ignore the stuff about the apples and you try and just concentrate on the numbers. For example, it's possible to learn how to drive a car without knowing how every part of your car works. The next computational thinking concept is called decomposition. Now, decomposition is really nice because it does exactly what it says on the tin. When something is decomposing, it's breaking down, and that's exactly what you're doing to a problem. If you've got a big problem and you break it down into smaller subproblems, each subproblem is just easier to solve. For example, if you think about making, for example, if you think about making your breakfast and you break that down from it being, this big problem, having a cup of tea and a slice of toast with jam on it. If you break that down into its component parts, each part of it seems really easy to do. I mean, anyone can slice a bit of bread, anyone can toast a bit of bread, anyone can butter that toast, and anyone can add jam. But put that all together, and that makes toast, and that makes part of our breakfast. Now, try and imagine this as a computer game or a big programming module that we're working on. Teams of people can work on little parts of it that make up the big part of it. So that is why decomposition is a really good tool to use. And the last thing we're going to talk about is something called pattern recognition. Like I said, it's not necessarily one of the conversational thinking concepts that we need to know about, but it does help us to see trends in the things we're doing and be able to reuse parts of code whenever we need to, thus making it more efficient.